just going to start off by acknowledging the other people who worked on a lot of the structure effort recently. One is Chris Toney, who's really vital for working with the FIA data. Joel Connett, who's going to be speaking a little bit later today, who's here, and Curtis Nelson, who's back in Sioux Falls. So I'll be talking about vegetation structure, which for LANDFIREs always involves sort of an amalgamation of both the height and the cover product. And of course, our focus is mostly on fire behavior and fire analyses. For various reasons, structure can inform us about transition from surface fire to canopy fire. It can also tell us about wind coefficient reductions and all that. But there's other applications, as Matt alluded to this morning, that also are that also apply the structure information that we can derive from LANDFIRE data. Ecosystem health and successional stage is directly linked to height in particular, but also canopy cover. Habitat mapping, looking at subcanopy airspaces, is linked to structure and how material is distributed within the canopy. And certainly climate and energy balance issues are as well. For example, biomass, which is highly linked to carbon studies, biomass is very highly correlated with height. So if we can have height maps for the country, we can also start looking at biomass maps and get an idea of how much carbon is there and sort of answer the carbon sequestration and flux questions. So this goes beyond just fire applications. And we're seeing the data used for these as well. So there's other people who are interested besides the fire community in what we have to offer them. So I'll start off talking about the LANDFIRE National existing vegetation height product. Height is mapped by life form with decision tree models. And Don largely alluded to this in the preceding talks. We talk about life form, which is basically tree, shrub, herbaceous, map that across the landscape, and then use the field plot data as well as other Landsat imagery, the three dates of Landsat imagery, DMs and derivatives such as slope and aspect, and any other ancillary data that might be available for us to use to map height for these three life forms across the landscape. I just kind of wanted to point out our legend for existing vegetation height as it stands now for the lower 48 and for Hawaii. Herbaceous and shrub classes break down pretty well, but if you look at our tree classes, especially in that very also important 10 to say 50 meter category, those are pretty large, broad classes. And that's largely defined by what we were able to do with the data that we had in hand, especially considering that the only remote sensing data that we used was Landsat imagery, which is a two-dimensional depiction of what's on the surface instead of a three-dimensional picture. In Alaska, or even, at least for our tree class, is even broader. It's either less than 10 meters or greater than 10 meters. So not a lot of detail, not a lot of definition there. For the national existing vegetation cover for the forest or tree class, we basically directly took the outputs from the NLCD forest cover. Didn't really do much to that other than really just import it into the LANDFIRE product. Shrub and herbaceous cover were estimated from field data representing an average values of 30 meters to correspond with our Landsat pixel size. We used regression tree versus decision tree modeling. So for the modeling portion, we mapped cover continuously and then binned it into 10% increment classes across the landscape. We had some end-user observations, one of which was that forest height values tended to be too low. Forest canopy cover values tended to be too high. I'll go into a little bit about why this might be the case. And that this had a significant impact on fire behavior modeling systems. And so the decision was made to basically remap forest height and canopy cover for the conterminous US. So again, just forest, not shrub, not herbaceous. We really didn't touch that. It was the forest products that we looked at again. We said the forest height values tended to be too low. Part of that is going to be how we derived the metric from the field data. Part of it's from the field data that were used. Part of it is, as I alluded to before, the remote sensing data that were used to derive these products. Again, we use a two-dimensional Landsat imagery to derive our height products. The forest canopy cover, as I said before, was derived directly from the NLCD data. And there we have to look at how they generated their product, which was pretty much solely a remote sensing based product. They scaled from high resolution imagery to Landsat imagery. So from their whole product is basically looking down on the forest from above. And it looks like what some people want, or what users want, is something that depicts more a field-based estimate of where you're estimating cover from below. And if you just think about it, it's going to look different. Your tree canopy is going to look different whether you're looking at it from above versus whether you're looking at it from below. And that's pretty much what we captured in this 2 high. It's not an indictment of the NLCD product. It's the way it was established. So for the LANDFIRE Refresh, we again used a regression tree modeling approach. That didn't change. And we used FIA-derived values of forest site and canopy cover. So only FIA data, no other field plot data were used in this process. And there was a bit of a refinement to the way the FIA data were used to especially generate the canopy cover products, which I'll show in the following slide. Landsat imagery, that stayed the same, or 3 dates of Landsat imagery, and it was the same data set as was used before, and the terrain data as well. For the height mapping, we incorporated the shuttle razor topography mission basal area weighted height product that was developed by Joseph Kellendorfer and colleagues at the Woods Hole Research Institute in Massachusetts. I'll talk a little bit more about that in the future, but that is a good reference. Kellendorfer 2004, if anybody's interested in this, they really describe their process very well. So for deriving the field-based estimates of canopy cover from the FIA data, what Chris did was basically take the STEM maps that are provided with the FIA plot data and then used 2 forms, or used line intercept method that the Interior West FIA region uses to get canopy cover for saplings, or for trees greater than 1 inch in diameter, including saplings, to generate canopy cover. And then for larger stems, applied regression equations first to predict crown width from stem diameter, because crown width wasn't measured in the field, and then used geometric models to estimate canopy cover from those predicted tree crowns. So it's very much a bottom-up look at how to get canopy cover. And now to talk about the SRTM height product. The shuttle razor topography mission flew in, I believe, February of 2000. So it was a one-shot deal, flew for 11 days, used both C-band and X-band radar. And it, as the name implies, it was a topography mission, so it was trying to look at surface topography. But radar signals convolve with vegetation and its structure as it is on the ground. So you can get a vegetation height signal from that. It's not going to be the top of a canopy. It's going to be something within the canopy. And that within canopy height is going to be dependent on the arrangement of your canopy material, how dense it is, how moist it is, both within and if there's any surface moisture. But they were able to do, excuse me, a lot of tuning with the data. Basically took a simple difference between the SRTM elevation product that they had and NED and got this sort of SRTM height product, which they then correlated to a series of FIA derived height metrics and found that they could get a pretty good correlation between a basal area weighted height and their SRTM derived height. So what we did is we then used this product that Joseph Kellendorfer produced and used it as another input in our decision tree modeling. And so the impacts of these, so what, when we compared our improved products to our national products, did we see or did it address any of the questions that the end users had raised? So looking at first at the forest height, and this is for those large geo areas that I think Don and Matt kind of alluded to earlier. I'm not going to go through them all in detail because we just don't have the time, but look at just a few of them. I do want to point out that the axis, the y-axis, that's a log scale shown that way, so otherwise we just have to have huge graphs to show all the information. And then the x-axis is those canopy height bins for forests that I talked about before. If you look in the upper left, that's where you have the Pacific Northwest. And again, one of the comments, and a lot of those comments came from early on in the process, and that's where we kind of started mapping. You'll notice that that upper height bin, greater than 50 meters, we really didn't have much in the initial product, which is the one shown in green. And then the refresh or improved, we have considerably more in that top category. And that geo area in particular is where you'd expect to see these really tall trees. Other areas don't show much difference, especially in the very tallest class. But if you do look at the red bars versus the green bars, you do see sort of a shift towards that higher end of the height spectrum across the board. It's even more apparent, I think, in the forest cover. There again, the original product, LANDFIRE National, shown in the green, and the refresh or improved product shown in this sort of brownish red. You can really see it, well, in the Pacific Northwest, North Central, A little bit less so in the northeast. We don't have quite the shift down in the range, but that's also where I'd expect to see the least problem, given that you have broadleaf forests, very dense broadleaf forests versus needleaf forests. So in general, it looks like the improvements that we did help address the comments that we got from the end users. Chris Toney is right now working on using new FIA data to sort of do a validation of this, more geospatial versus just looking at broad categories. So again, that's just focused on forests, and it just kind of focused improving that 2001 era data. So now we're kind of looking at updating to the 2008. And there we incorporated annual disturbance layers, both Landsat derived from the time series stacks, and also contributed data from land managers' polygonal data. And this is Joel's topic later on in the afternoon, so I'm not going to say any more to that. But these data were used to define where we would want to make the updates or where you want to make the changes. And existing structure was updated based on predetermined vegetation transitions. And for forests, I used FES and FIA data to model 10 years of growth for various vegetation disturbance combinations. So the type of disturbance and the magnitude of the disturbance, and also the vegetation type that it occurred in. And also, given that we're looking at a nearly decade-long time span, vegetation structure is going to change even if there is no disturbance. You're going to see growth, succession. So FES was also implemented without incorporating disturbances to determine vegetation transitions in undisturbed areas. So that took us to 2008. So now we're looking towards the future. What are we going to do as our next step? I think this is the most interesting part of it. We're starting to look at integrating other data sets besides, or at least as far as other remote sensing data sets besides Landsat, looking primarily at LIDAR data. LIDAR data provide observations of canopy structure more or less directly. They loan themselves especially well to the type of information that we need to have. So studies that have used airborne data for deriving canopy structure are out in the literature. Anderson et al. In 2005. We have a paper coming out in February. There's others in between. Really show how these data sets can be used for the type of products that we want to develop. But for the airborne data sets that are out there, for projects such as LANDFIRE, one of the definitive characteristics of LANDFIRE is supposed to be this nationwide consistency. What we stumble into is the fact that we do not have airborne LiDAR data sets across the entire country. This is sort of an illustration of data sets that are currently available. This isn't an exhaustive list. There's more there, but the gaps are large. The gaps are far larger than the data acquisitions. Not only that, the data acquisitions aren't always ideal for vegetation analyses. A lot of them were collected for bathymetry and coastal studies. A lot of them were collected for right-of-way analyses and civil engineering projects, so not necessarily vegetation studies. But the data sets are growing, they are being collected, and they're being collected with greater consistency, which is also a vital characteristic to look at with LiDAR data. Older data sets in particular, you can see huge discontinuity in quality between older, one data set collected for one project and data set collected for another. So there's a lot of processing involved to make them useful. That's changing. We have more of a standardized product now, which makes them a lot easier to work with. But still we have the gaps to deal with, which is something we don't really want to have to address. So we looked at the one data set that was available for the entire country as a Spaceborne LiDAR data set. And I don't know how many people here are familiar with ISAT GLAS, but it's freely available. As the name of the satellite, ISAT implies, the instrument was not developed for vegetation studies. It was developed for cryospheric studies, but still, we've been able to use it pretty exhaustively for height and biomass analyses, so we thought we'd try to incorporate it here. The ISAT satellite was launched in 2003. It was decommissioned in August 2010. The last laser actually failed in 2009, so the data are no longer being collected. It's a waveform LiDAR. It's not a discrete return the way a lot of airborne systems are that most people might be familiar with. The footprints are very large compared to the airborne systems, 65 meters in diameter. The footprints are spaced 72 meters apart nominally along track, so it's not continuous data. It's along orbital tracks, separated. But all in all, we have almost 2 billion measurements made over the entire world in that time period. So it's a pretty rich data set to be working with. There are issues with the data. You can have saturation of the waveform for various reasons. Something that's actually fairly easy to detect. There can be anomalies and outliers that, these are data that you wouldn't even want to work with. Other issues that we would need to consider if we want to use the data, because of that large footprint, we have to worry about heterogeneity of land cover within the footprint. You could have a footprint, that's half forest, the other half could be in the lake. It's not necessarily a problem, but you need to account for that. You can also have disturbance since time of data collection. Data collected in 2003, you could have disturbance if you're going to use it for subsequent mapping. Clouds are an issue. This laser functions in the near IR, so clouds are a problem. And slope, that large footprint, slope becomes an issue. Not good. This is going to work. I was worried it wasn't. I'm going to illustrate this because there's actually things that we can do about correcting slope. It doesn't mean that you have to throw out those data. When you have fairly homogeneous stand on a fairly flat surface, with these waveforms you get a very strong peak towards the bottom, down here, which is your ground, and then the rest of it is shown in the upper part of the waveform. And where the X is, it kind of marks where the top of the canopy is. If you have slope, it's still going to register where you have the top of the canopy, but that ground signal becomes more distributed as it hits that sloped terrain. So if you were to compare these two waveforms to each other, you're going to see there's this elongation of the waveform. That's not the only effect that slope can have. It's a primary one. The neat thing is there are things that you can do to correct for it, but you need to know it's there. The first place we're really going to start integrating the GLAS data is in Alaska, partly because of the wealth of data. Because of the orbital tracks, you have higher density up towards the poles, so we have a lot of data, over 1 million shots in forested land. It hasn't been quality screened yet, but even if half of those go away, we've got a lot of data to work with. And also because we don't have a lot of structure data, plot data in Alaska. So this is a great place to really start testing this out. And working with another project with another researcher at AROS, we've done a lot of work in the Yukon Flats ecoregion of Alaska. The big river is the Yukon. Fairbanks is about down here, where the helicopter is. And we used the GLAS data and then used a decision tree modeling approach because, again, the data aren't continuous, and Landsat data to generate the spatial product of height. And by and large, we're pretty happy with the patterns we saw. We have higher heights near riparian areas, which makes sense. But then we have these splotches, the lighter greens, showing lower heights. Well, why? Does that correspond to anything? Lo and behold, they match up very well with the MTBS fire perimeters, which is encouraging. It was sort of a sanity check on what we had done. Does this make sense? Also, the overall scale from 0 to 33 makes pretty good sense in Alaska. You're not going to have, as you get down towards Sitka, you're going to have big ones, but not necessarily where we are. So overall, we were pretty happy with this sort of preliminary product. And then, kind of to carry that on a little bit further, we did do a couple of FlamMap modeling runs with the original LANDFIRE inputs and then also GLAS-derived inputs. I have to think this example, the GLAS-derived inputs didn't just incorporate height, it's also canopy cover, and canopy base height and canopy bulk density derived from GLAS. You can see there's a difference between the two. I'm not going to say which is better. I'm just going to say that when you incorporate these data, you do see a difference. So we want to understand why, what's driving that. Kind of just leave it at that for now because this has not been quality assessed at all, but you can see that it does make a difference. That's about it for the GLAS data. One thing people keep asking is now that the data are no longer being collected, what can you do? There's going to be an ISAT-2 follow-on mission. Right now it's scheduled for launch late 2015, maybe 2016. It's not going to be a waveform instrument. It's going to be what they call a photon counting instrument. The application for vegetation is still being worked out. It is, again, geared more towards cryospheric sciences, but we're hopeful that there's a lot that can be done with this different type of instrument as well, and that we might be able to incorporate that into our future mapping. The other thing that we're doing is starting to find ways where we do have these discrete sets of airborne lidar data to start folding those into LANDFIRE products as well, at least for those local applications, or at least allowing people who have those data available be able to fold them in if they need to. And that's it.